Today we are taking you through the basics of probability. And this will be the agenda for today. We'll talk about the probability in data science. Probability is applied in so many fields, but our focus today will be a bit diverted towards data science. And we'll talk about some basic rules of probability. And we'll delve into some common distributions, and we'll give some practical examples of instances where probability is applied. So, probability in data science. What is probability? So, probability is the chance that something will happen. And that's a general explanation to that. The probability that something will happen. So, for instance, if it rains today and it rains tomorrow, what's the probability that today being Saturday, tomorrow being Sunday, what's the probability that it will rain on a Monday, or it wouldn't rain on a Monday? Maybe it will be cloudy or it will be sunny. You might not know. Probability is the only way that can help you tell and be able to predict if it's going to rain or it might not rain or it will be sunny. And so with the formula I have here, probability of an event here is a subset, any subset E of a sample event. That is an event. A sample space is like the total number of possible outcome of an experiment or an event. So when I say an experiment, it's not necessarily going to the lab to perform an experiment. An experiment can be even throwing of a die. When football, they're about to start playing the match, they have the toss of a coin. So one side of the team chooses head, the other side of the team chooses tail. So each team has the same probability of being selected. So that's half. It's probably that if you get a head or a tail, or a head or a tail. So when they toss the coin, when it gets to the head, then whoever chooses the head or whichever team chooses the head kicks the ball first. So a probability or an experiment is anything happening. It could be whether it will rain or not. It could be having a die and then rolling a die, a six-sided die. It could be anything at all, not only going to the lab to perform an experiment. So the set of all possible outcome of an experiment is known as the sample space, which we are going to use S, and then the subsets of this sample space, we are going to use E for it. So for instance, if I should toss a coin, a head or a tail, a head is one possible outcome of this experiment. My experiment here is tossing a die. One of the possible outcome I can get is getting a head. The other outcome is getting a tail. So the probability of any event or any experiment at all is the outcome, the number of outcome, especially what you are interested in. Then you divide by the total number of outcome possible. So probability and uncertainties. Why probabilities? Is probability really needed in AI? Is it really needed in data science? Is it important? Yes, it is very important. Everything we do depends on probability, because you might not know what will happen in the future. Today, I might say I want to be a data analyst or I want to be a data scientist. But what are the chances that you actually be a data scientist in 5 years to come? Assuming you are in class 6 or you're in the university and you are studying statistics or computer science or AI, and you want to be a data scientist, what are the chances that in some 5 years to come you will truly be a data scientist, or you're going to divert into a different field or career? So probability is used in everything we do in our daily lives. In everything we do, probabilities and uncertainties. something could happen that you didn't actually prepare for, and that has happened. And those are uncertainties that we can't actually control. So probabilities are very, very important, especially in building models, because when you build a model, we train a data set and you want to build a model, you use probability to actually decide whether this model is a good one or this model is not a good one. Is it that it is okay, it is overfitted, it has underfitted? You look at all this depending on the probabilities that you compare, and then you're able to tell whether um, this model is a very good model or this model needs some small adjustments depending on the probabilities that you get to find. So attaining perfect accuracy is not expected. You can't get 100%. Assuming you want to train data sets to be able to predict whether it rains or fall, you will not attain 100% accuracy. And so we know that since we can attain 100% accuracy, we have some small probability left to cater for the unforeseen circumstances or other uncertainties that could come in. And you realize that most of the data sources we even take online has some kind of noise in it. And when I say noise, it means maybe there's some missing data, there are some incorrect spelled values, or sometimes a whole like row will have any values at all. And so these are things that could also contribute in getting some uncertainties, because you as assuming you go to the field, you take some data, you're supposed to take data of individuals. There are some days you might go into the household, you wouldn't meet anybody in the house, and so you leave all that places blank. Or assuming you go to them in the house and you're supposed to take maybe their phone number, or they're supposed to take their emails, they're supposed to take other data, but then the person does not have a phone number. So what do? You need to leave it empty. The person does not have an email. Not everyone has email, so you need to leave that empty. And so when they are done taking the data and they bring it for you, the data scientist or data analyst, to actually analyze it, maybe have a models created from that, they're going to have some empty or incomplete coverages. And you have to, sometimes if it's quantitative, then you have to either use the mean and other central tendencies to be able to fill in those empty spaces. Or if you can't actually do that, if it is qualitative, then you might have to take all the row out, if only it's not going to affect the modeling. And so probabilities, we can't do away with it. It's very important, and that is how come we are treating probability at this time in our AI journey. So we're going to go straight into the basic rules of probability, and we have a lot of rules, but I didn't want to go really in depth because it can be a bit confusing. So I spoke about, or I selected few that I could use for the explanation. So one of them is that probability of an event is always between 0 and 1. There's no cases that you have a probability greater than 1. It is never possible. It's either the event does not happen at all or the event happens. And so it's really it's falling between 0 and 1. And the probability of the sample space, which is the total number of possible outcomes you could have, is 1. So if you have a lot of outcomes or possible outcome, when you sum everything up, it should give you 1. The highest you can go is 1. So that's also a basic rule of probability. So if you go and then you're performing an experiment, or you're having a model and you're getting probabilities above 1, then know that there's an error somewhere which needs to be fixed. And also for any sequence of mutually exclusive events, when I say mutually exclusive events, it means events that can happen at the same time, 2 events happening at the same time. So when I say mutually exclusive events, E1, E2, the E3 to some En. And in that case, the 2 will be 0 and I cannot be equal to J. When I say I cannot be equal to J, assuming you want to label each events 1, 2, 3, I shouldn't be equal to 2. 2 shouldn't be equal to 3. So these two independent events shouldn't be the same. And so the probability of you joining, or probability of each event when you put them together is the same as the sum. So you realize that probability of into bracket union 1 to some infinity of an event EI is the same as summing each probability from 1 to that event. So when I say E1 union E2, is maybe probability, assuming I will always want to use examples so that you don't make it doesn't look so abstract. So I'm a science student and I read biology. At the same time, I read chemistry. So it's the electives are there. As a science student, you have the choice to choose which electives you want to do. I'm interested in maybe biology and maybe chemistry. So I'll do biology, I'll do chemistry. We have physics classes there, we have elective maths and so on. Some students might not be comfortable with elective maths and they want to do maybe biology and elective maths. So for me, I'm doing I'm doing chemistry or I'm doing physics at the same time, but someone else is doing e-maths. So when you union them, I happen to be someone or a data point in chemistry union physics. So someone who does only chemistry and maybe doing e-maths, then that person will only be at e-maths and I will fall between the two because I'm doing two courses. So this is the same thing applied here. The probability of number of students doing both courses is the same as adding probabilities of each. Probability of chemistry, probability of e-maths, probability of physics, if they put all together, it's the same as the union of each of them. And so there's also one basic rule of probability. And the final one is E complement. When I say E complement, it's like not E. So if I'm reading data science and someone is reading, for instance, I can say data analytics. So if I have someone reading data science, then the complement of it is data analytics. And this is based on the assumption that maybe in that particular classroom, they are teaching only two courses, which is data analytics and data scientists. So those who are in data science class automatically are not in data analytics class. And so the complement of an event is 1 minus the probability of the other event. So probability of being in the data analytics class will be equal to 1 minus probability of being in the data science class. So this is also another brief basic rule of probability we all have to take note of. So this index explanation into mutually exclusive versus independent events. And independent events are same as the mutually exclusive. So mutually exclusive indicate that two events cannot happen at the same time, which I initially explained. It can't happen at the same time. And then independent events or non-mutually exclusive is the probability that one event does not change based on the outcome of the other. So if I said earlier, if I'm in a data science class, then that means I'm only in a data science class. I cannot be in a data analytics class. So that will be a mutually exclusive event. Either I'm in one, I'm in the other. Either I'm a girl or I'm a boy. You can't be a girl and a boy at the same time. So these are events that there can't be any intersection. But however, non-mutually exclusive events, which are also independent events, are cases where you can be in one and also be in the other. So as I said, if I'm assuming I'm a science student and I chose to be in a biology and chemistry class, then I fall in between this shaded area because I'm reading biology might be A, and then I'm reading chemistry is B, so I'm here. But however, in these cases, if the school or the university teaches only data science and data analytics, and you're supposed to choose between each of them, which of them you want to specialize in, then this is the case for A, being data analytics, or being in B, which is data scientist. There's no way you can have you can be in these two classes. It's impossible. You need to choose one, and that is it. And I'll talk about conditional probabilities and independence. For an event E and F, you can choose any alphabets for events. You can choose A, you can choose B, you can choose A subscript I, A subscript, anything. Just that you need to understand whatever you are denoting for that event, so that when you are using it in your proofs and in your calculations, it's not going to be confusing. So event E and event F, assuming we have two events E and F, the conditional probability of in, given that F has occurred, is denoted by probability of E. Then we have the I don't know what that sign means, but we call it, I don't know, I'm sure there's a different name for it, but this is E given F. E given F. So there are some cases where probabilities change, especially when there are cases that the two of them will happen together. So what's the probability that it has rained today? It will rain today, given that it rained yesterday. So these are conditional. One of the conditional depends on the other. It depends on the other. That means they are dependent. If they are not dependent, then it's going to be straight away. If you look at the second point, probability of E and F happening together is the individual probability of E multiplying the independent probability of F. But there are some cases that when you want to calculate the probability, it's depending on some factors. So if you use this formula, it might give you some errors. So you have to go ahead and use this formula. Probability of an event E happening based or dependent on an event F is equal to the joint probability of the two divided by the probability that is depending on over here. So probability of E given F is probability of the joints divided over the probability of the event that is dependent on. This can also be called marginal probabilities. The top will be called joint probabilities because there are two. You could have events E, F, G, D happening together. They are all joint probabilities. That's like 4 different events happening at the same time, and it's possible. But in this case, we are using only 2 events, and this is something that can be also, it's expandable. This is just for 2 events. There are cases when you can have like 3 events, and 2 events are dependent. 2 events happening is dependent on 1 event that has already happened or yet to happen, and so the formula keeps changing. But this is the basic formula you can use if you are supposed to calculate any a probability of an event happening given some event that has already happened. So with that example, I can say, okay, assuming, a family where they have cancer. So if I want to now have, and there are some families that do not have any history of cancer at all, but some families have history of cancer. So if you want to find a probability of, assuming me being part of that family that has cancer, probability of me having cancer, it will be calculated based on some history, because my family has some history and some traits of cancer, and so it's possible that my probability of getting a cancer in that family is very high because I have some traits of cancer in my family, and it will be higher than someone who comes from a family that do not have any cancer traits at all. So these dependent probabilities and conditionals are something that we can't do away. There's always a reason and something dependent on an event that we always have to take into consideration. And if we don't take it into consideration, we might be giving a wrong answer or misleading probabilities, which in the end it's possible that no one will believe if you should give any probabilities like that. Also, this condition is equivalent to probability of E given F equals E. So this is the case if they're independent. If one event does not affect the other event, then our probability of E given F is just probability of event E, because this time our event F is not affecting the probability in any way. So automatically, if E and F are independent and do not depend on the other, then probability of E given F is just probability of E, and vice versa. Probability of F given E is equal to probability of F, because E is not affecting event F in any way. And if this should happen, then we can say that probability and E and F are independent. So sometimes when you get a question, they'll ask you to calculate the probability of E given F. They'll ask you to calculate the probability of E, and then they'll let you find they want to find out if these two events are independent. Or a question comes, a real life time question comes, and then you calculate the probability of an event E and another event F, and you realize that these two events, when you calculate E given F and E, they are the same. So this should give you a hint that, oh, if these two probabilities are the same, then these events are independent. One doesn't affect the other and should be treated as such. So if the events E and F are independent, and if knowledge of the occurrence of one of them does not affect the other, then we will say that they are two different events and they don't depend on each other. So now I want us to have a short quiz. This is just a theoretical approach to be able to let all of you have meanings into whatever models you are going to be creating or modeling. It will give you an insight into whatever you are doing. And so this is just a basics and a theoretical aspect to get you to understand what probability and how important probability is in modeling. So we'll have this short quiz, and we'll continue to the next session. So we are going to do this together. We are going to pick the question one after the other, and then we are going to solve it together. But before we solve it together, I'll take the question one after the other. And if you happen to solve it, you can drop it into the chat box. Then I'm going to check the chat box to see if we have some right answers coming in. So we'll take it one after the other till the fifth question, and then we'll continue just to know that we are on the right path. Okay, 1/2 half 0.5, right? Great. So that means that you understand what I've said so far. So we'll take it together. All of you are right. So for the first question, when rolling a fair six-sided die, what's the probability of obtaining an even number? So when you take a fair six die, a die has sides 1, 2, 3, 4, 5, 6. And the probability of obtaining an even number. So 1, 2, 3, 4, 5, 6 is our sample space. These are the total number of events you could, events you could have in this experiment. Our experiment here is rolling a fair die. So the possible number, or the total number of possible outcomes you could get is either a 1, 2, 3, 4, 5, and then 6. So we want to find out the probability of obtaining an even number, and we know in this sample space 2, 4, and 6 is an even number. So what we are interested in, so right now obtaining an even number is not our probability of success, or say probabilities of obtaining an even number is what we are interested in. So that is going to be 3, and then the total number of possible outcome you could have is 6, because you have 1 all the way to 6. So 3 divided by 6 automatically gives you half, and that's 0.5. So we are going to go to the second question. What's the probability of an impossible event? So as usual, I have 5 people commenting in the chat box. Okay, 0, 0, 0. Whoa, I'm seeing a 1. 0. Okay, right. So the right answer is actually 0, because the probability of an impossible, when we say an impossible event, there's no way that event will happen. There is no way. So an impossible event could be, for instance, me going to, say, Lagos, traveling to Lagos, and then traveling to Abuja at the same time. There's no way I can be in Lagos and be in Abuja at the same time, unless virtually. But in person, there's no way. So this is an impossible event. And so the probability of you like getting this event is 0. There's actually no way. No way. So I'll say these 2 instances. Yes, so this probability are 2 different instances, and you can't have an intersection. You can't be in Abuja and be in Lagos at the same time. So there are 2 independent events that one do not depend on the other. They are 2 dependent, and so it's 0. So what does probability means? I know. So impossible event. Even if I sleeping right now, yes, it's not possible because my eyes are widely open and I'm talking. There's no way I could be sleeping and teaching at the same time. It's possible. I have some people who, especially how do you call it, drivers who sleep and drive at the same time. It's amazing, but I don't know how to do it. But that should be an impossible event. So then the third question: what does probability mean? Let's drop our definitions of probability in the chat box. Let's drop, let me get like 5 of the responses. What does probability mean? If anyone should meet you somewhere, or your nephew niece should ask you what is probability, how are you going to explain to them for them to understand what probability is? Probability might be a big word, but giving it to them or explaining it to them in like low term for them to understand possibility of an event happening. Okay, probable, likelihood of an event. Yes, is the framework for thinking about uncertainties. Right. Uncertainties. So probability is probable. It might happen or not. You don't know your chances. You are traveling. You're on the flight going to UK. You're on the flight going to US. What are the chances that you get it there safely or not? These are uncertainties. There's no way you could say that, okay, I will get there or I will not get there. Some people travel by air and then they get into planes and air crash, and that is it. But you are so sure that you are traveling to UK, but these are 50-50 chances. You might not know whether you get there or not. So you will have that probability that it's possible that I'll get there safely. It's possible I will not get there safely. So these are uncertainties that actually happens, and that is what probability means. If you build a model, it's possible that the model will be accurate or not. There are cases that the model will not perform at all. Some of the models will outperform. So that is when they do that's the overfitting. So you have to adjust the parameters again for it to, perform normally. And so these are probabilities that happen anytime. And the level of probability, because probability is ranging between 0 and 1. So if it is 0 and then moves to 0.1 and it moves to 0.2, then you can tell, okay, this model is not doing well. But if the probability is like 0.9, chances that whatever you have trained the model with, it has predicted the same thing, then you can say, oh, then my model is a very good model, because after training it, I have a 0.9 chances that it will predict exactly the same thing. So this is something you can actually say that, oh, my model is a very good model. But if you train a model and your model is predicting like, say, even half, is okay. But if like 0.2, 0.3 chances that whatever the model has predicted is not, or just like whatever the model has predicted is just 0.2 chances of like correcting, then that is like a no-go area. You have to really check it. So the third question, we are going to unbiased coins are tossed. What's the probability of getting at most 1 head? So let me see the answers in the chat box. We'll quickly finish this. Okay, saying 1/4. Okay, let me have some more. 1/2. Okay, 0.75, right? There's a variability. I'll call it variability in the answers. Different sets. So this is like variable. They are not close. They're like different. So let me have like two more. We have half, we have 1/4, we have 0.75. Any more? 3/4. Okay, that's the same as 0.75. Great. So we have 1/4. I can see some correct answers and the rest are wrong. So we'll take it together. So the right answer is actually 3/4, which is 0.75. Right. So let's go into the explanation. Okay. So two unbiased coins are tossed. So I have 2 coins, and each of them would have either a head or a tail. The other one will also have a head or a tail. So now, first of all, you have to look at the sample space. The sample space is going to be the total number of outcomes. So this time I'm having 2 coins in my hand and I throw it. So the possible outcome is that it's possible I can get a head and a head. It's possible I can get a head and then a tail. And it's possible I can get a tail and a head for 2 different coins. And it's also possible I can get all of them being tails. So I have 4 possible outcomes: a head and a head, a head and a tail and a head, and then a tail and a tail. So right now that we know our possible total sample, now we are interested in the probability of getting at most 1 head. So 1 head should be in any of the samples. So if you check the 4 samples, yes, at most 1 head. So that is like 1 or more heads. At most 1 head. Yes. So getting at most, oh, I'm not getting the explanation right. Let's see. At least 1 head is 1 head or more. At most. Okay. So at most is the vice versa right now. So the most you should get. Okay, if that's the case, then I'm going to say those who had the right answer shouldn't be 1 or less. Right. So at most 1 head. Okay. So that means those who selected half had it right. Yes. So Ario had it right. Elijah had it right. Oye Layo had it right. Cool. So at most 1 head is either a tail or a head in each of them. So you realize that head is present in head tail sample and also present in tail head sample. So that's going to be 2/4. So 2/4 is going to give you Elijah says glory. So 2/4 is at half. So that's our right answer. And our final question, assuming we have a probability, and I learned this math in school. Okay, so if probability of C is 5/3 and probability of D is 7/3, and the joint probability is 3/3, we're supposed to find probability of C given D. So these are conditional probabilities. So per our formula, let's answer this and then we quickly move on to the second part of the studies. So let me see the answers flowing. About 5 answers, 2/13. Okay. Let's have some more, like 5 of them, and then we go ahead with the discussions. Okay, our time is running fast, so we'll continue. So probability of C is 5/13, and probability of D is 7/13. Okay, I'm seeing a 5/7. Probability of C given intersection D, which is like a joint, is 3/13. So you're supposed to evaluate probability of C given D. So you realize that in this case, these events are not independent. One is dependent on the other. These two events, one is depending on the other. So probability of C given D, I'm saying 3 or 7, right? So probability of C given D is equal to the joint probability, which is 3 on 13. And then I remember saying that when you have the joint probability is divided by the probability is depending on, which is this D right here. This D right here. So 3 on 13 divided by 7 on 13. So automatically then we have 3 on 7 then. So Akim is right. 3 on 7. Akim is right. So I hope you all understand the basics and some few basics of probabilities. How it's okay. I used C divide condition D times probability of D equals. And what did you get? In 4, TT has no head. In 4. Oh, you mean question 4? Yes, TT has no head. Yes, but our question says at most one head. At most one head. This is getting confusing now. So when we say at most one head, what does it really mean? I know at least one head means one head or more. So at most one head, maybe any of you can unmute and then explain to the class. Because if we get a definition right, then we can know what probability it is. At most, maximum. Oh, maximum. So which means that 0 is inclusive, having no head in. Okay, so that still comes back to my answer being 3 on 4. 3 on 4. Then those who had a half, you're taking it back. The correct answer goes to 3 on 4. 3 on 4. So our probability with probability of having a TT, probability of having a HT, and the probability of having a TH, then divided by the total probability. So then we have 3 on 4, which is 0.75. 0.75. This one is purely English. If you understand the English, then we should find the probability. It's a formula word. Thank you so much for bringing it to my attention. So our final answer still goes back to 3 on 4, having either a tail, a head tail, or tail head, because we want at most one. So either no head or one head. Right. So we move on to the fifth one. So the fifth one, as I said earlier, the answer is 3 on 7. So we quickly move back to our lessons. We are done with this brief question. Thanks for participating. Right. So now we're going to move a bit deeper. Don't be too confused or don't be stressed by seeing like big formulas. These formulas, I mean, ChatGPT and all that have been made easy for us. So don't stress too much, but just get the idea behind it, the idea behind each distribution. So when you are faced with a real life problem, you know what distribution to use, you know what to do. But with the hard formulas, I mean, if even if you use Python, we have all these distributions embedded in it. So you just have to call a particular library, then you can use it. They've already coded everything for you. So you just need to understand how it's done. If you want to do purely research, then maybe you might take this very like important. But if you want to practice, then you focus on like understanding the idea behind each of them. So we'll go straight into random variables. So when we say a random variable, a variable English definition means that something a container, kind of like a container. If you have a bucket at home, you can choose to pour even buckets. I want to use something you can, yes, let me use utensils. So if you're cooking, you can choose to pour water in utensils today. You can choose to pour maybe food. You can cook food in that same utensil. The next day you might want to fry chicken and then pour in that utensil. So that utensil becomes a random variable. It's not fixed. Today it can hold water, tomorrow it can have chicken in it, tomorrow it can have fish in it. It's depending. The same utensil used to cook different types of food. So that utensil, I'll say, is a random variable because it's not fixed. It's not fixed. I'm tempted to say maybe a bathing bucket will contain only water because there's no way you go and bath with oil or bath with any concoction, but water. So if it is just water, then I can say that is a fixed variable. But a random variable is something whose value is not yet known. It can change. It varies. It's something that changes like very quickly. So it's not fixed. And so to be able to understand what our distribution means, we have to talk about random variables to be able to understand the name behind it and why it is being used. So we have two types of random variables. The first one is a discrete random variables. These are random variables that take only discrete numbers. So countable possible number of values, possible events, maybe 1, 2, 3, 4, 5 events happening. Assuming you go to the roadside to pick a car, you can count the number of cars, passing in, let's say, in 1 minute, how many number of cars passes a particular junction in 1 minute. And so this time is countable. It's either no car, 0, 1, 2, 3 to some infinity. So if there are cases that they are the random variable involved are discrete, then we say that it possesses countable number of possible values. In there are cases also that is continuous. And so if it is continuous, then it also exists random variables whose set of possible values are uncountable. They are infinite. You can't count them 1, 2, 3, 4. It's continuous. For example, if you finding the weights of students or even the heights of students in class, when they stand on the weighing, whatever they call it, it can be 50.1. Tomorrow you can stand on it and it will be 50. In some 6 months, you go and check your weights, it has moved to maybe 60.3. The next time you check, it is 60.8. So those ones are not fixed. They are not discrete. There's no case you get like 50 on points and get 70. The same with height. If you check the height, today you can be this number of meters. The next day you go and it's something with points. So these are continuous random variables. So these are the two main types of random variables. So continuous random variables can take like decimals and all that, but discrete takes only like countable, which is 1, 2, 3, 4. Now you go straight into probability mass function, and for short we call it PMF, probability mass function. And probability mass function is for discrete random variables. When you hear probability mass function, the first thing that should come into your mind is this PMF takes only discrete random variable. It takes only 0, 1, 2 to some infinity. This random variable cannot take negative. It can't take decimals. No. Continuous variable can take negatives. It can take decimals because it's a continuous. Between 1 and 2, we have values between 1 and 2. Between -1 and 1, we have values between -1 and 1. But discrete is just like 1, 2, 3. So when you hear PMF or probability mass function, the first thing that should come is this random variable takes only discrete, and is denoted by a small p into brackets x. In this case, our x is random variable, a discrete random variable. You can use any alphabet. You can use A, you can use B, you can use C, anything. Just know the definition for each alphabet you choose for it. So in my case, I'm choosing X. So x, I'm defining x to be a random variable, a discrete random variable to be precise. So my PMF is going to be small p of x, and normally, generally, the PMF is always denoted by smaller p so that it doesn't confuse you when you get to the cumulative side. So smaller p is for PMF. And then this is the same as probability of x equal to 1x. These two things are the same thing. So the sum of all probabilities is equal to 1. So initially we talked about probability ranging between 0 and 1. If the event does not happen at all, then it is 0. If it happens, it is 1. So the sum of all probabilities should definitely be equal to 1. So when you sum over the values each PMF should have, you should get 1. And then we have expectation. Expectation is the same as the mean. So in high school, we're taught about the central tendencies. We have expectation, which is the same as the mean. We have the mode, we have a median, we have standard deviation, we have variance, and all that. So in this case, we are looking at expectation. So expectation is the mean. Something you expect something to happen. What's your expectation? So, for instance, when you're about to have this class, you have an expectation. You have certain standards that you want to meet. So, when you're done with the class, you want to, check yourself and check the class and, evaluate the class and find out, okay, were my expectations met or not? So that is what expectation comes in, and just like the mean. So the formula for that, I didn't do a lot of formula work because it can be a bit complicated. So expectation of x is the sum of, you're going to multiply x and that probability of the events. So this is the formula for it. So if that MF has values from 1 to infinity, then you're going to sum from 1 to infinity. And then if you pick it one after the other. So for instance, if you have values, say 1, 2, and 3. Okay, let me just use 1 and 2. So if I toss a die, or yes, I toss a die, or maybe I toss a die, that'll be 1/6 for each of the events happening. So we have 1, 2, 3, 4, 5, all the way to 6. So you want to find the mean of just one die being tossed, and that die being tossed is a probability that you might get that particular value. So that's the mean, the expectation that if I take this die right now and I toss it, the mean, or I should expect this number, is an expectation. I should expect it. So if you want to calculate this, each probability has 1 on 6. So you're going to do, for the first one, 1 times 1/6. Then you go plus, then you pick 2 times 1/6, then plus 3 times 1/6. 1/6 is the same for each. So you're going to do that so you get to the sixth one, 6 times 1/6, and then you sum all. When you sum all, that value is the expected value you should expect when you toss a coin, or toss a coin. Or in this case, we are using a die. So when you toss a die, and we also have the variance. And the variance, we have expectation of s squared minus the mean all squared. So note, these are two different things, the s squared and the mean all squared. So the same way we have x, and x is reflecting here as x. When you want to do x squared, you have to also put x squared here. This time it should have a 2 here. The 2 will be here. So for instance, if I want to find the variance, first of all, I have to find the expectation s squared first. Then when I've already found the mean, I can just do that all squared. So if I want to use the same example, then I'm going to do 1 squared times 1/6. Then I'll move plus 2 squared times 1/6. Then 3 squared times 1/6, all the way to the sixth one, 6, the sixth one squared times 1/6, and that will give me my expectation of x squared. Then now I plug it in here and then find my variance. And the standard deviation is the square root of variance. So some examples of cases where you can do PMF is the Bernoulli distribution, binomial distribution, Poisson distribution. We have geometric distributions. There are a lot of them, and these are distributions that have been discovered so many years ago. They look at the situation of a particular event, and they're able to monitor and see that, okay, this particular event, this is how it behaves. And then those who brought this idea, they named it after themselves. So if you're able to come up right now as we are here, ChatGPT was not even here so many years ago. But if you're able to come up with a new distribution, you can also name it by yourself, provided it's legible and is approved. Then we can also start using it. Instead of you starting from scratch, you will just go straight into using your distribution. So these are distributions that some people over the year have researched, and they've realized that this is how each of them works, and it has been in use for so many years. And so we'll take each of them. I didn't talk about all, I just talked about 3 or 4 for each distribution. So these are just examples of some of the distributions for PMF. So anytime I say PMF, what should come into your mind is probability mass function, and it's for discrete random variables. We'll move into probability density function. When we say probability density function, or PDF, what should come into your mind is continuous random variables. So we are going to define the PDF as f of x, and it's the same as p of x equals x. It's the same thing. We are choosing, you can use any alphabet. Bear in mind, you can use any alphabet. If only you understand what it means, you are good to go. But these are alphabets that has been used for quite some number of years now, so it has come to stay. But if you want to choose your own alphabet and use, please go ahead. If that will make you understand better, go ahead and then use it. So we are using F to denote anything PDF. We are using P to denote anything PMF. So in this case, f of x, we are using that for PDFs. And also you realize that we said in our basic rules of probability that it should fall between 0 and 1. And if you sum the sample space, you're supposed to get 1. So when you are summing over a number of random variables, then we are going to use a capital F for it. And then when you are summing over, when you are having just for 1 point, then you use a small f. So in this case, we are summing from minus infinity to infinity of a probability f of x, and then you should get 1, because that's the maximum you can get. When you sum all the sample space, the probability of attaining each of the possible events in the sample space, it should be 1. You can't go beyond 1. So we are just applying the basic rules to this one. So the same way we did for PMF, expectation is x times the PDF. Now this one, we use the ds because we are going to integrate. I believe all of you have math background, integration and differentiation. So in this case, we integrate from minus infinity to infinity of x times f of x, and that will help us get the mean. And the same way, when you want to find the variance, then we do the x squared. So wherever you see the x over here, you're going to square it. Then you do your math integration, and then it gives you the expected value or the variance. So it's the same idea from the PMF, just that in PMF you are summing, but in PDF you are integrating. And you can move from a CDF to a PDF when you are using continuous random variables. You can, if you have a CDF, you can differentiate. I hope I'm getting it right. You can differentiate to get a PDF, and then when you have the other one, you can integrate to get it. So variance, and then we have examples of distributions that have the continuous random variable that take unlimited values. So for instance, we have uniform distribution, we have normal distribution, we have exponential, we have other ones that I didn't mention here, but these are just a few of PDFs that when you come across, you know that okay, these distributions take only continuous random variable. It can't take like countable. The countable is inclusive. It takes over a number of values. So it can take 1, 2, all right, but it takes numbers between 1, 2. It takes negatives. It takes like decimals. So this is just a fair idea about what PDF and then PMF means. And the difference is whether it's continuous or a discrete random variable. Now, finally to the CDF. CDF is the same as cumulative distribution function. And CDF is of a continuous random variable x is given by f of x. So I initially mentioned that cumulative in this diagram, you are summing from some negative value up to a value. You are summing between two numbers. You can sum from 3 even to 5.5. You can sum from 1 to 3. You can sum from each point to each point here. So over here, since we have f of x, we are summing from minus infinity to some x, which we don't know. So if I choose x to be 1, then I'm going to sum from minus infinity to 1. If I choose x to be 2, then I'm going to integrate from minus infinity to that 2. If I want to integrate between two values, say capital F of A minus capital F of B, then I'm going to integrate from A over here to B over here. So f of x simply means like from negative to that value. And the same way you can apply that for discrete. This discrete, that one you are summing from say some 0 to some x. X can be 1, 2. X falls in the real numbers. It can be 2, it can be 3, it can be 4, it can be even to infinity. So this is a general formula, and all these formulas have already been embedded in Python. It has already been embedded. So all you have to do is import that library, then you call the name of the distribution, and then if you want to find a CDF of that distribution, you just call the however it's done depending on the syntax. If you want just a point, which is small f of x, you also have a way you do it, and then gives you that probability. So this is just to give you an idea how it's done, and this is a graph. So assuming I want to sum from minus infinity to some 3, then I'm going to integrate from minus infinity to 3 of that particular PDF because this is integration and this is summing over infinite numbers and not countable. So this f of x automatically should tell you that this is a PDF and this is not a PMF, right? So now we are going to pick a sample of each distribution one after other to understand the idea behind it, to give you an idea of how to tackle practical questions when they come, or as in when it presents itself, how to go about it. So with the discrete distribution, I'm taking Bernoulli and binomial to start with, and an experiment whose outcome can be classified either as a success or a failure when performed is termed as a Bernoulli. So I can say that tossing of a how do you call it, a coin is a Bernoulli experiment. It follows a Bernoulli distribution, because if I I'm defining that. And you have to take note of what you define as your success and what you define as your failure. If I'm saying, if I get a head, I mean, we all want to be the head and not the tail. So if I'm defining head as my success, if I don't get head, then I failed. Okay, it's possible you can also define the tail as your success and then the head as your failure, but it's up to you. You need to understand how you define each of the parameters that you use. So when I say parameters are just like the standard tendencies. It can be mean, it can be standard deviation, it can be counts, like the total number of counts or the number of times an event is performed. Those are parameters. So if I say parameters, what should come to your mind? It should be either a mean, it should be a standard deviation. They are central tendencies. It shouldn't get you confused. So depending on how you define your parameters, you should know how to use each distribution. So if I define head as a success, then since I have equal chances of getting a head and a tail, then my probability of success is half, and my probability of failure is also half. So here my P is half and my Q is half. Okay, and then this time, because I'm tossing a coin only once, then I have one showing here, which is the one here. Okay, so I have probability of 1. That means x equals 1. And when x equals 1, x is P, and x is 1 because of its success. And if you get x equals 0, then that is the failure. If I toss the coin and I get 1, you can toss a coin several times. If you toss a coin several times, then that becomes a binomial distribution. That becomes a binomial distribution. But if you toss a coin once, then it's a Bernoulli. It's either you pass or you fail. It's either you write a test, you pass or you fail. It's simple. It's a Bernoulli distribution. And if you write several courses, if enrolled in several courses, several AI courses, maybe computer vision, AI, deep learning, blah, 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 NLP, and each of these courses, when you write the exam, whether you pass or fail, is a Bernoulli. But if you put all of them together, because you've written several courses, and then each of the several courses you've written is either you've passed or you failed. So if you put all this together, that gives you a binomial distribution. That gives you a binomial distribution. So X actually counts the number of successes here. And since Bernoulli is performed just 1, then we are going to say that it's a x equals 1, then that's it's a success, and when it is 0, it's a failure. So for Bernoulli, our probability of having a success is P, and then our probability of failure is 1 minus P, which can also be denoted as Q. So as I explained to the binomial have parameters N and P, and N and P simply means the number of times that experiment is performed. So if you enrolled in 5 courses, then your N now becomes 5 because you've enrolled in 5 different courses, independent courses. They are not intertwined. You can't have the two at the same time. Independent courses, then now N becomes your 5, and then your P becomes your half because it's either you pass or you fail. It's either you travel or you don't travel. You jackpot or you know jackpot. You can't have in between. So it's either a fail or a success. So this is the PDF for binomial. It is similar to Bernoulli. If I take n combination I out, n combination I, this time I'm choosing I instead of x. So don't be confused. I can still put x here and represent this I by x, and represent this I by x, and represent this I by x, and change this possible values you can take by x, and is it the same thing as this? So if I put one combination 1 and I put one combination 0, it's still 1. So automatically you realize that the PMF for Bernoulli will just be P and then 1 minus P, and then 1 minus P all the to the power 1 minus I. So wherever you see n over here, if you put 1 inside this, you get a Bernoulli distribution. If you perform it a number of times, you get a binomial distribution. And the expectation, this has been proved. It's a long proof to get here, but we are not interested in the proof. So just keep in mind that if you have any practical example looking like a binomial distribution, then the expectation is the number of times you performed that experiment times the probability of success. And the variance is NP 1 minus P. 1 minus P is the same as Q. So it can be NPQ. So that's the variance. So we will take some practical questions to get to understand more. We'll move to discrete distributions, different distribution called Poisson. This Poisson distribution has this PMF looking like this. This is exponential to the power minus lambda x over x factorial. This distribution takes values from 0 to infinity. So here our parameter is lambda. If our parameter is A, we're going to change all this lambda to A. If it is B, we'll change all this lambda to B. So if you are saying Poisson is parameter B, we will come and change it here. Okay, so the idea behind this is modeling the number of times an event happen over a period number of over a given time. Okay, so for instance, if I go to the bus stop and I'm counting the number of times, I give myself 10 minutes. So at each 10 minutes, I count the number of times a car will come and pass. Each 10 minutes, I count the number of times a car will come and pass. This is a typical Poisson distribution. It focuses on counting the number of times an event will happen in a particular period of time, general for any case. So this practical example here is seeing the number of customers entering a post office on a given day. You can be a number of customers entering a bank. So you can go and sit at the bank. You check, okay, from 8 a.m. to 9. You want to see the number of people that enter the bank. You want to check from 9 to 10. How many people enter the bank? You do that to like maybe 4 to 5 in the evening. So now you can even use this to tell the rush hour, the time that when you get to the bank, stop. You go and keep long over there. Depending on the number of people who enter there and the number of time they wait. The waiting time is even another distribution. We'll get there. That will be the exponential distribution. But the counts, the number of customers entering the bank, if you realize that between 8 and 9, a lot of people enter the bank, I don't think you want to enter there and go and waste a lot of time. You want to look at the time that a lot of people don't enter the bank and then go there, just have your transaction and you're out of there. So these are practical examples that is used in the bank, the finance, when you go to pizza joints, the supermarkets, they use Poisson distribution to model the number of people entering into the bank and the supermarket or bank at a particular time. And they can use this to predict the number of times. So if for some 1 month, they've consistently monitored and realize the number of people, the average number of people entering a bank or a supermarket at a particular time, they can use that to predict for the next month. And if they see the differences, because obviously during Christmas time, a lot of people will enter supermarkets and maybe banks more than normal time. So they can use that to predict different seasons and times of the day. And that will give you an idea and give you an idea of how and what time you want to enter the bank to reduce the number of people you go and meet there. So if you hear anything like that, that is a typical Poisson distribution. Now with the geometric distribution, this is the PMF, sorry, for this geometric distribution. And 1 minus P is a failure and P is a success. If you do the proof is going to give you 1 over P. And this proof starts from that formula I gave you. You sum over 0 to infinity. Then you're going to pick 1. If you pick 0 times, then you come and put this PMF there. Then you put the value of 0 inside plus 1. That's the formula they use to achieve this. You can try it in your free time. And then they use that same formula that I gave earlier for variance to get this. So this one is this is the number of events happening until otherwise. So suppose that independent trials, each having a probability P, P is between 0 and 1, obviously, and of being a success. And this success is performed, are performed until a success occurs. So I want to use this for example, writing GRE. GRE, I don't know why I fear to write GRE, not for any reason, but one, because the English words are too big, and because you have to pay a huge amount of money for it. Like, I just don't want to write it. I always dodge anything GRE, but it's something I have to overcome. So assuming you're writing GRE, you failed several times. You are failed. You write and you fail in quotes. It's not okay. Let me not use failure. Let me use success. If I use success, it will not sync well. Let me use failure in quotes. You failed several times, and finally you wrote it and you passed. You can see that you can say that it's a geometric distribution. Okay, you have written a lot of courses, maybe university courses. First semester you passed all your courses, you passed. Second semester, same, until one particular semester you failed. That is a purely geometric distribution. So the number of times an event happen, number of successes until a failure happens, or number of times failures happens until a success happens, then this is a purely geometric distribution. Okay, then now if that scenario is given to you, then you can say, okay, this is a geometric. So instead of you coding from scratch, you just come and pick this distribution because it has already been done for you. You know the variability that comes with it with respect to the variance, you know the expectations, you know everything. So a practical example is the number of balls randomly selected onto a black ball is obtained. So you have a box of red balls, black balls, green balls, yellow balls. You randomly pick one ball, you bring it out. You didn't our success here is a black ball. You're defining black ball as our success. So anything else is a failure. So you pick the red ball, you look at it, it's not red, you put it back into it. You pick another one, you bring it out, it's yellow, you put it back. You pick another one, it's green. You continue that number, you continue picking until you pick a black ball. And if you finally pick a black ball, then that is a typical geometric distribution. I hope I'm clear with this. So, Elijah, you can go ahead and ask.
All right. My question is with respect to the geometric distribution. Now, you mentioned that, like you said, that number of events until otherwise. Now, if for instance you mentioned the issue, maybe the black ball you mentioned now. Now, that's what we're looking for. Is a focus on the number of times you're able to get the failure event before the success. Is that the focus of geometric distribution? Like the
Yes,
number of
times.
Just the fact that I just want to get the black balls. Or is it the focus on the black ball? The number of times to get there.
Number of the times you have to pick before you finally pick whatever we are interested in. So the number of times we can use that to model. So even if I use GRE also as an example, you can classify Africans or even classify Ghanaians, and then pick a data of all Ghanaians, the number of times they've tried to write that GRE and failed, until they passes. They're going to count. They're going to use that count, and they'll use the average to tell that, okay, if a Ghanaian wants to write GRE, this Ghanaian is going to have a highly possible, or is expected to write GRE 5 number of times before they can finally pass. And they're going to make a lot of money from that. They'll make a lot of money from that. So that helps them to actually know the amount of money they can get from each country, because the number of times you try until you finally hit a success. Exactly. Number of visa application before getting the visa. Exactly. Number of exam written. So you apply for so many things, and sadly, you have to go through some number of failures before you get that success, and that helps in prediction. Okay, focus is on number of counts. Thank you so much. So for answering this very important. So go ahead.
Now,
Our time is
my
catching up.
the way it's coming now, I'm just don't mind my thoughts. That with this issue now, means this can be actually programmed in a way that for instance, maybe I'm doing a business now, and everybody wants to come in. I can program that, okay, maybe let people try for like 5 times before they could be able to have access to it. And that, I don't know, do you get my point? Like
when you program it that way, then you are actually controlling it from your end.
That's what I'm talking about now. Like when you're using ML to control human behavior.
Exactly. So you control it from your end. So no matter if you only give it the parameter, maybe you want them to try 5 times before getting in, then everyone is going to try 5 times before getting in, because you have programmed it like that. So we'll go ahead with continuous distributions. So first of all, we'll talk with the basic, which is the uniform distribution. Uniform distribution, a random variable is said to be uniformly distributed over an interval alpha and beta. So alpha and beta can take any number, can be between 0 and 1, can be between 0 and 3, can be between 1 and 4, any number. And the PDF is represented by this. So if you're able to know your parameter, if you set your parameter to a particular beginning and end, then you just slot in your values here, and then that will be the PDF. The mean of this PDF is the alpha plus beta, the sum of the two parameters divided by 2, and then this is the variance. This is the variance of this distribution. So to get this one too, you have to do the proof, which I've not shown here. You can go online, you can get it online, but we are not so much interested in the proof. So I just put the formula there to be able to guide you get it. And so in practical situations where you can do this or apply this is randomly, sharing a group uniform. There's no bias. It must not be biased. So if I'm sharing a group 1 and 2, I can write A, B a number of times and just put it down for everybody to pick. Everyone has equal chances of selection. Everyone has equal chances of selection, and then pair whatever you select, you automatically group into either group A or group B. So this is a example, very simple example of continuous uniform distribution, which is a continuous random variable. So I was asking a question there, what do you think the CDF of this PDF will be? Want to find a CDF of a PDF, you integrate. If you have a CDF and then you want to go back to PDF, you differentiate. So anyone can drop the answer in the chat box. What do you think this CDF will be? Differentiating from alpha to beta of 1 over b minus alpha. This will be for the math students, those who like math. So if you integrate this, if I integrate this from alpha to beta, if I remember my math concept, anything constant, we push it out of the integration box. So we push 1 over beta minus alpha outside. So we are going to have only 1 over here, and then when you integrate 1, you get x. So then if I'm going to slot from alpha to beta, then that's going to be beta minus alpha. So then I'll have x over beta minus alpha being our CDF. So the CDF of this PDF is going to be, instead of 1 here, we'll have an x over here, divided by beta minus alpha. Okay, we'll continue with the next distribution. So this is a normal distribution. This is a PDF of a normal distribution. It has a very nice formula, a bit confusing. I don't focus on the formula yet, because most of the time we use the standardized normal distribution. So that makes the formula a bit easier. But this is a normally distributed random variable with parameters mu and then sigma squared. Sigma squared means your variance, and then mean means your expectation or your mean. Okay, so all this you see over here is the variance, it's a formula work, and then the mean. This is how the PDF looks like. So as I said here, the expectation is mu, and the variance is sigma squared. So if x is normally distributed with parameter mu and sigma, then x minus mu divided by sigma is normally distributed with parameters 0 and 1. So the 0 and 1, that's I said earlier that you want to standardize it. If you want to standardize it, and that is what we use most of the time, because we have a z table that you convert all your x value to a z, and there's a formula for calculating that. So you use that to calculate the standardized version of it, and then you're able to read easily on the table. If you go online and you type z table, you have a feel about it. You see how it looks like, and then you apply it. So let me give you a brief reason why we want to use a normal distribution. A normal distribution is very key. We use that mainly and a lot of times when modeling and training our models. Okay, most of the assumption you need to be able to how do I put it? Assumptions you have to meet before you can actually use a particular distribution or apply a particular set of distribution is for the fact that it needs to meet a normal distribution. It needs to be normally distributed. The errors needs to be normally distributed. So with this, normally normal distribution comes to play when and normal distribution is a bell shaped. Okay, we can have it skewed to the left or right, but normally naturally it comes as a bell shape. And sometimes when you model, you train your models, and then you want to compare the predicted value to the actual value, assuming you are modeling let's say you want to predict prices of um, items. Okay, you have to make sure that the error you get should be normally distributed, and normally distributed in the sense that the error, which is the residual, the difference between the actual value and the predicted value. So when you train the model, then you have your training sets and your test sets and all that. You compare to see if whatever you've predicted is what is having as the actual. So you have a different column for your predicted value, and you compare to the actual. You find the difference between them. You have to make sure that the difference between them is normally distributed. Normally distributed is a condition you have to meet. So if that error is normally distributed, then you can go ahead with your model, because the errors that you got are normally distributed, and normally distribution is key. You can't have everything like you can't get everything 100%. You can't get everything accurate 100%. So when it's normally distributed, it's something we can take into consideration. And so this is one of the cases you can use a normal distribution, the difference between the estimated value or the predicted value and the actual value. This is also used in chi-square. Chi-square also compares the estimated value and the actual value to see if it is follows a normal distribution and is independent of each other. The categories are independent of each other. So normal distribution is used a lot, not only in machine learning, but other. So this is the formula I said earlier for converting normal distribution to a standard normal. So a standard normal has a z-score from minus infinity to positive infinity, but most of the percentage lie between -3 and 3. So assuming this is the population, to be able to read the probabilities on the table, you have to first convert it. And when a normal distribution is given to you, it comes with 8 parameters. It comes with a mean, it comes with the standard deviation. So with the mean in mind, you know the mean, and you know the standard deviation. It comes when you know the variance, you know the square root of the variance is standard deviation. So you use that to convert the x to z, and then you have it transformed into the standard normal, and then you can use this to read from the table and get your probabilities to either reject or accept an hypothesis. So normal distribution is used in so many ways, as I said earlier, and it's very important and key in making decisions. The next continuous distribution I want to touch on is exponential. So this is looking like Poisson. The only difference between Poisson and exponential distribution is that whilst Poisson is interested in the number of counts, exponential is interested in the waiting time. It's interested in the time that one has to wait, or the number of time that one will have to, continue to observe something before it actually hits a success. Okay, so the main difference between exponential and Poisson is Poisson is interested in counts, as our brother asked earlier. The counts is the number of times you have to do something to achieve a success. But in this time, exponential, we are interested in the waiting time. Okay, the waiting time, and this is how the PDF is looking like. This is how it looks like if exponential distribution have parameter lambda. This is the PDF of the PDF of the exponential distribution, and it has mean 1 over lambda, and then the variance is 1 over lambda. Earlier in Poisson has the mean and the variance being the same. Mean and variance be the same. So Poisson has expectation being lambda. If lambda is its parameter, then the variance is also, I think the variance is lambda squared. Let me quickly check. The variance is, okay, the variance is lambda. All right. So has the mean and the variance being the same, but this has, so exponential is interested in the amount of time, whilst Poisson is interested in the count. That's one key difference between the two. So we move on to the next session. So these distributions are foundational in various aspects of data science. Whether you are exploring data, whether you are doing hypothesis testing, whether you are modeling, you are predicting, understanding these properties actually helps you to make informed decision. So before, even as a data analyst, before analyzing any data, you have to look at the distribution of each of your columns, your variables. Look at how each of the points are distributed. If all of it are normally distributed, then you can go ahead with your analysis. Else, you might have to fine tune to be able to reach a normally distributed, curve before you can proceed in analyzing and making insights. And it goes along the same way from hypothesis testing, where you have to have your null hypothesis, have your alternate hypothesis. You use these probabilities and distributions to be able to read the probabilities on the table, or if you want to use your calculator to calculate it too, you use it to be able to help make informed decisions. So probabilities are used everywhere, directly or indirectly. Every day we apply probabilities. Okay, so our final session, example applications. I believe explaining the individual probabilities, I've given like several applications, but we'll still take a few, and we'll have our final quiz, just a short quiz. It has like very simple questions, so you don't have to do so much calculations, and then we bring our class to an end. So example application. So for instance, with the normal distribution, I think I mentioned this earlier, predicting house prices using linear regression modeling and tool, if I may say. So with this one, if you have you want to predict house prices, okay, so house prices here, automatically we can say they are continuous random variables, and linear regression actually comes with, it has a particular formula that you put a lot of factors. Maybe you want to consider the location of the building, you want to consider um, the area the building is located in, the shops that are around it. You want to consider several factors, okay? The materials that were used in building, how decorated the rooms are. Is the room tiled or not tiled? Does it have the bath in the room or outside? Like a lot of factors. So you look at prices for other areas, and then now you want to model for a particular set of data. So you have your actual value, and then the linear regression is going to help you get a value, like a predicted value. Okay, so this will help you in modeling, because sometimes not all the variables are necessary. Not all the variables are actually important in modeling. So if you have, like, say 10 variables together, if you model using the linear regression formula, which is also embedded in Python, it will give you significant values or p-values for each of the variables. So we have a threshold. If it is less than, maybe say 0.5, most time we use 0.5 as alpha, which is this, we use that. And if it is less than a particular probability, we say that, okay, this is really going to contribute to the house pricing. If it is more than this number or more than this probability, it's not going to contribute to the price, and it is not relevant. So variables that are not relevant, we have to take them off the model, so we can now provide space for variables that contribute to the pricing. The variables that are only contributing to the house pricing are the ones that we are finally going to maintain in our model. So with this one, normal distribution comes in, as I said earlier, when you're able to compare the residuals to see if the residuals are normally distributed. Okay, so one of the assumptions, or the um, how do I put it? One of the things that needs to be met before you can actually use a linear regression model is for the residuals to be normally distributed. If the residuals are not normally distributed, you cannot apply linear regression. Okay, so with linear regression, if you check your predicted values and your actual values and they are normally distributed, then whatever conclusions you can make from the model, the linear regression models, they are valid and can hold. Else, you have to try other ways to be able to make sure that the residuals are normally distributed. The same with binomial distribution. An example of binomial distribution is conversion rates. Okay, so predicting conversion rate of a site. So if 100 people visit an online store, and 40 out of the 100, 40 of them make a purchase, then you can use binomial distribution to predict the probability of different number of conversion for the next 100 visitors. Okay, so now our probability is going to be 40. Our probability of success is going to be 40 over 100. So when 100 people visit the website, only 40 make a purchase. So 0.4 is going to be probability of success, our n being 100. So we can use this to check the probability, and we can predict for the next 100 visitors who visit the website. Same with Poisson. Poisson also focuses on the number of calls. So focusing the number of calls at the call center at a given interval. So if an average of 3 calls comes in per hour, you can use Poisson distribution to predict probability of receiving, say, 15 in the next hour using the formula. So an average of 3 calls shows that our mean is 3 and our parameter lambda, if I might choose for my parameter, will be 3. Okay, and then I'll use that, I'll slot that into the formula, and then I can use 15 as our x to find the probability of the probability that we could receive 15 calls in the next hour. So this also helps with predicting number of calls at call centers. Geometric, we also have modeling the number of trials before a user clicks on an advertisement for the 3rd time. So if I'm on Instagram and then we have page advertisements, so most of the time you might not want to open any advertisement. You see any advertisement, you just scroll, then until you come to a particular advertisement and you are interested in what they do, and then you stop to read what it's all about, and then you perhaps click on it. Then this follows a geometric, because most of the time I don't open advertisements unless it's like very, very important to me. So the model or the AI is able to know that, okay, these are the particular things you are interested in. So things that you don't click on, it will not show those feedback to you again. It will only show you advertisements on things that you are interested in, because the number of times like you've bypassed a lot of advertisements to click that particular one, that should tell me that you are interested in it. So it's going to only show advertisements that are similar to that particular one you clicked on. Multinomial distribution, also using NLPs, predicting the next word in sentence. So now if you are typing in email and you start with I am, it's going to predict some number of words to use. Maybe I'm fine, I'm going to the hospital, I'm traveling. So when you start with I am, it predicts some number of words, and this one is multinomial distribution. So this is like an advanced level of binomial. Binomial means like you have only 2 outcomes, but multinomial means like several outcomes. So maybe if I'm typing I am, maybe I have I am hungry. So hungry, I'm traveling, I'm working, I'm eating. So all these possible outcomes are different outcomes. Okay, and the idea and the distribution behind it is binomial distribution. That is how come you're able to start typing and we could predict the next word that you'll be interested in typing, or you are coming to type. And finally, with these 3 examples, we have the chi-square distribution. I didn't talk about this, but this is also a type of distribution, and this is using feature selection. So determine the number of occurrence of certain features is independent of class label. So if I want to do classification projects or modeling, like identifying whether an email is spam or not, and also finding out if there are certain words contained in this email. So let's say a word containing like lottery or win or congratulations. So you want to compare the number of congratulations or win you see in the ones that are actually not spam and the ones that are spam, okay, and see if they are independent of each other or not. So in this case, you use chi-square to be able to test whether they are the spam, the win, whether it's spam or not, and then win or congratulations or not congratulations is either independent or not, and it can help you with your modeling. And with uniform distribution, we use that for normally splitting into training and test sets, because that one is random. When you give it the data, automatically, if you give it the percentage, maybe 70% or 80%, however you want it, it will randomly distribute and split it into 2. So the logic behind it is uniform distribution. Okay. And then finally, exponential distribution. You can use this to predict lifetime of machine parts. So a machine part will continue to work car parts until one day you spark the car and it's not working. So now use this distribution to be able to find the average lifetime of the part in 2 years. And this is used in a lot of organizations. When you buy a car, okay, this is the lifespan, this is the average number of time you can years you can use it. They use exponential distribution to be able to predict it. So you know that, okay, this car can last for 5 years, this car can last for 2 years, this car did not have a long lasting. So this exponential distribution is the idea behind all this that we do. So this is what I have for you today, and I believe you've understood everything I've said. If you have any questions, you can ask. And then these are the resources I used. A first course in probability by Sheldon Ross. And then this is a link to a website. And the final one is a YouTube channel, has a playlist of probability stuff. So your free time, you can also go there and then go and learn more. So thank you so much.